Good morning, students. Today, I will talk about a very important issue related with the microscopy work, okay? And this part of the microscopic work is usually not taken in account as deep as it needs by the conventional users, and then what you get with this is some frustration about your results, and then usually people abandon the technique. But there is the need to put some effort in sample preparation to get good results. It's very important to keep it in your mind. It's not just all the theoretical understanding and practical understanding operating the machine, but also in sample preparation. This is fundamental to get a good result. Okay? The outline of my presentation is this. I will discuss first the criteria for successful TM sample preparation, and then I will go to the description of some techniques. I will put some examples. They are very limited by the possibilities that I have to present here, but you have plenty of opportunities in working in your samples. Not just what I will present here, that is what is in the books, you understand. You need to do by yourself. And then I will present here some reference about this and talk about suppliers of material for sample preparation and so on. Well, why we need to put some efforts? Why you need to be worried about sample preparation? You are learning that electrons have properties of particles and waves, and then because of this we have a strong interaction between the electrons and the material and the sample, the atoms in your sample. This will cause the scattering of this original electron beam, and this will form the contrast and so on that you have in your image. Okay? And then to have a specimen for TM, you need to have it transparent for the electron beam, because you are looking in transmission. You need to make to be sure that the electrons will be able to pass through your sample. This is the idea. Okay? You need to have an intensity of these transmitted electrons, okay, to have good contrast in your image. This is very important. In the majority of the materials, we have this number here, 100 nanometers of thickness. That is the ideal sample thickness. Smaller than this is better. Thicker than this is you start to have some limitations. It's not impossible to work with a sample that have more than 100 nanometers in thickness, but you will deal with many problems related with multiple scattering and so on. And then the interpretation of your image will become more difficult, not just, not that intuitive interpreting, but you need to take into account the idea of multiple scattering and so on. The thickness of your sample, the the excellent thickness of your sample will depend on some factors like the materials properties related with the atomic number, the mean atomic number of your sample, related with density of your sample, the crystallinity or not, and so on. The acceleration voltage of your machine. If you have a very high acceleration voltage, you have a deeper penetration of the electrons in the material. But on the other hand, if you have smaller acceleration, you have more scattering of the electrons. And and the requirements for the investigation method that you plan to do with your sample. If you want to do use spectroscopy in your sample, it's completely, it's very adequate to have a very thin, as thin as possible sample, because the multiple scattering will make your spectrum very difficult to be understandable, okay? But on the other hand, if you just want to make bright field images, you can deal with samples that are thicker than the ideal situation, okay? Well, as I told you, the criteria is related with the electron scattering inside your material, okay? Here, we have a silicon sample, okay, just a drawing. Here we have a bulk material, we have here the accelerating voltage of the electron beam of 100 keV, okay, in all these simulations. In this situation here, we have the bulk material. We have a very thick part of the silicon. You can see here that the 100 keV electron beam will penetrate your sample as deep as about 50 micrometers. Okay. When you go to TM specimen, you have a thinner sample, and then here you have 200 nanometers, and comparing with a sample of 50 nanometers. You can see that the scattering of the electron beam will cause the electron beam to open, to scatter, okay, and the full width at half maximum with a sample of 200 nanometers will be 12 nanometers, and with a sample of 50 nanometers you have just 1 nanometer, okay? And then I can ask you, which sample you prefer to have a very high resolution? It's very simple to understand it. With this, with a thin sample, you have a smaller scattering of your electron beam, and then as a consequence, you have for sure a better image. And then, as I told you, to get this kind of thickness in a sample, it's not really easy. You need to put a lot of effort. Okay, the simulation is very clear, but in practice, to you to have a very small, very thin sample is very difficult. This is why not everybody have this ideal situation. Many people work in a not that adequate situation. Okay. Here we have some. We discuss some requirements on your own sample preparation. Your sample preparation technique must not affect what you see or measure, or if it does, then you must know how. All the sample preparation techniques, you need to cut your material, you need to crush material, you need to make it thin. If you have a part with a bulk material, I want to do microscopy here. Then I will need to get this and cut it to make it thin. And then I will put a lot of forces, and I will change. Perhaps I will change the material. And then it's very important that when you start to prepare your, when you choose your sample preparation method, that you know in which way you are affecting the structure of your material. It's very, very important, this. we must not change the material properties, like the structure. Material may be amorphous, polycrystalline, crystalline. If you want to characterize, to show exactly these characteristics of your material, you cannot change it before to put in the microscope. And also, it's important to take in account that the chemistry of your material may change when you apply some method for the sample preparation. Okay, the composition of the bulk material, when you do an analysis, elemental analysis, you have a composition of your bulk material. But when you make it very thin, very small parts, this distribution of components may change because of the migration of some elements to the surface or to the core of the material, and so on. It's very important to be sure about what you have, and in each way your material is changing. Okay? Here it's very clear how the sample preparation method will impinge some artifacts in your sample. This is very important to be clear, to have it in your mind. All that you do will change. Your sample will change in some way. It's very important to understand in each way it's changing, but you need to have, to be sure in each way it's changing. Okay? And then the criterion for the appropriate technique is the smallest change, influence in the structural and chemical properties of your sample. This is very important. I mentioned it yesterday about the need to the researcher to know very deeply about the sample, the properties of your sample, before to go to the microscope. As I say to you, if you are choosing a sample preparation technique, and then in my case yesterday, I saw that the sample was with XRD. I saw that the sample was crystalline. I saw that I had different kind of metal distribution, metal oxide in one sample, not any non-metal oxide in the other. And I did some XPS surface analysis. And then I learned that my sample has a distribution of elements, a specific distribution of elements in its surface. This is very important before choosing which kind of sample preparation technique you use. Because if you are dealing with the structural properties, you need to do some high resolution TM or do the diffraction and so on. By dealing with the chemical properties, you need to do some spectroscopy, and the sample preparation may be different in this way. And then it's very important to you to know what you want, the information that you want from your sample, before to choose. It's important to have all this information of your sample as a way to choose the way you will prepare your sample. Okay? So let's continue. We may have different types of sample, okay? We may have bulk materials. We have a part here, a brake of a car. You may have interested. You may are interested in understanding the changes that you have in structure, in the physical structure here in this part, and then you need to have all these parts to go to the microscope, and then how to deal with this. We have also layered structures as semiconductors. We have many examples of layered structures. Semiconductor here for a solar cell. You may have non-transparent particles for electrons. We have particles and they may be non-transparent or transparent for the electron. The two situations are a little bit different, the way you will prepare. This kind of sample, they are not transparent. Here you have 5 micrometers in the middle of one of these particles, and then for sure you need to cut it to have a transparent, electron transparent sample. In this case, the particle simply goes directly to the microscope, and you have transmission through the sample. Okay? To go to the microscope, you can't put it inside the machine, okay? You need to cut and so on and prepare a sample. Which kind of shape you have. We used to have, all the microscopes have defined by the shape of the sample holders that the ideal sample will have a circular shape, okay, with a diameter of about smaller than 3 millimeters, okay, and a thickness that is smaller than about 100 micrometers. Why we have this situation? Because the space inside the polypiece of the TM, it's very, very small. It's very limited, and then we need to have the sample as small as possible to go into this gap between the polypiece and to the technique work in a proper way, okay? Related here with the maximum thickness of your sample, it is related with the position, exact position of the sample inside the TM column. As I told you yesterday, you have a standard focus of your objective lens, the best one, the excellent one of your objective lens. And you need to play with your sample through the object plane of your objective, okay? And by doing this, you have the space that you have, the range in height that you have to play with it, it's about 100 micrometers, okay? This is why if you have a thicker than this, you will not have anything. Well, I'm talking about the thickness of the sample edge, okay? If you have the very center of your sample needs to be electron transparent, okay? But the edges of your sample need to be smaller than 100 micrometers, okay? Well, then, as I told you, we have to understand exactly what we want about the use of the machine, what kind of information you extract from the TM investigation, okay, to define, to find the perfect preparation strategy, okay? What exactly what we want to see in our about our material? we try to deal with structural properties. We can determine the size distribution of particles or chemical domains inside the sample, and so on, okay? We may want to see about area density of some characteristic of the sample or around the sample. We may try to deal with structural defects. Perhaps you are interested in the chemical properties of your sample, and then you try to find about the composition, some modification that you have in the interface between different phases, the sharpness of the interface in between the different phases, different domains of your sample. You may try to go to have information in the electronic properties of your sample and magnetic properties. For each one of these requirements, we will try, it's more adequate to find a specific strategy for the sample preparation, okay? And then, as I showed in the last slide, we can divide roughly all the samples that we may have in these three types of samples, okay? The bulk materials, layered structures, and particles. It's a very good strategy to define how to prepare the samples, okay? And we need also to deal with material properties related, thinking about the sample preparation. The hardness of the material, because you may try to cut material, to crush material, and then you need to think if it is ductile, it is brittle, and all these material properties will put some limitations in the types of sample preparation strategies that you can use, okay? And also about the sensitivity to chemical solutions. Some of the preparation strategies will use some chemicals, and this is need to be taken into account. And then we can define our preparation strategy. Here, we have a flow chart that was prepared taking in account these three types of samples that we may have, okay? And it's very good to help us to decide which way to follow, okay? And then first, I will show something about layered structures, where you have here the surface interface of you want to characterize the surface or interface of a layered structure, okay? And then you can follow this way here to the microscope, okay? I will show in the next slides all these possibilities. You can, a layered structure, you may be interested in the surface. You have a layered structure, you may be interested in the surface or cross-section analysis. And then I will show something, a preparation of a quantum dot in a semiconductor, okay? Here we have information about the density of the number of these quantum dots in the material will affect the photoluminescence properties of the material. And then it's very important to us to understand in which way these quantum dots are distributed in the semiconductor, okay? Then which kind of experiment we may do. We may do something related with the plan view of the semiconductor or cross-section. What's the difference? By plane view imaging of this material, you have here the information on the area density of the quantum dots, okay? Then you can see the amount of the quantum dots that are deposited and related with the area of the material. You can see information about the lateral size of the quantum dots. You can understand, have information about the correlation, lateral correlation between the quantum dots, if they are scattered without any order, or if they have some organization. And you can see something about the morphology, if it is circular, if it is squares, and so on. By doing some cross-section imaging, we can have some different information. If you see the same material but in cross-section, you can have information about the height of the quantum dot, the width of the quantum dots, and in this case, it's important to be sure that you do not have two quantum dots, one behind of the other, because you are looking now in cross-section. And then if you have these guys distributed, if you look this way, you may have quantum dots superimposed, okay? Well, then I will show some strategy on how to cut the material to have information about this. Then we will have plane view and cross-sectional TM preparation. Okay. First, plane view. What we need to do to prepare this. You have the initial sample. We are interested in this green part here. What we need to do? We need first to thin the substrate. Okay. In this case of the quantum dot, you have the quantum dots in a silicon substrate. You need to thin the substrate first. Then you need to cut a disc. Why to cut a disc? To have the required 3 millimeter size in diameter, okay, of the material. And then you do the dimpling of your disc, okay. Then you have the disc with a small dimple in the center, okay. And then you can go to the ion beam milling machine to do the milling here in the center, in the very center of your disc, until you have electron transparency, okay. With this, we can see a plane view. From the top surface, we can image from the surface, and you have the plane view. For cross-sectioning, okay, we can do what? We start with initial sample. We cut it in 2 pieces, small pieces. We glue face to face. Here is the part where we are interested in. We glue these 2 faces here. We put this glued face-to-face sample inside a tube, okay, with more glue or resin, okay, inside a very small tube. Now we have a tube of 3 millimeters, okay, that it will be your sample in the end, okay. And then you cut this cylinder, this tube. It will be a cylinder. You cut very small pieces of this cylinder, and then you have a disc like here that we started, and then we start with the thinning of this disc to make it smaller and smaller, and then we go to dimpling this disc. We make a dimple inside the disc, and then again we go to ion beam milling, okay? And then we will have here in the center, in the very center, you have electron transparency, and you can see the cross-section of your material. Okay? Now I will show here I will talk about and show the instruments related with each of these parts of the preparation, okay? I will talk about the cross-sectioning preparation. Then we have here formatting for XTM, cross-section TEM. Well, here we have a machine, a wire saw, okay? Here you can see the wire, okay? With this wire, we can cut the sample that is here, okay? And then you come and cut it with the wire. Well, this wire is a wire of steel covered with diamond particles. Then it cuts almost all materials, hard or soft and so on. And then you cut the material, you glue. Here is the face, okay? You put it in the top and glue the two surfaces. You cut again these squares to be smaller than 3 millimeters to go inside the tube. Here's the tube. And then you cut this tube, small pieces of the tube in cross-section now. And then you have, you have these small discs with your sample in cross-section in the middle. But it's very thick, very thick. It's about 100 micrometers in this time. Then we go to the mechanical tinning, okay? With mechanical tinning, we have a polishing tool, okay, that it's a very hard piece where you put your sample inside a tube. You have here a sample holder, okay, and you have the possibility with this part here. It's a screw, okay. You put your sample there, and then you can go with the screw, putting your sample to the outside. And here you have very, very hard material, silicon nitride pads. This is a very, a lot with a high weight material device, okay, where you can go in the to make it you go in with abrasives, okay, to polish the material and remove part of these to make it thinner and thinner, okay? Then you do the polishing and you have the material as thin as is needed. Here you have a picture of the cross-section specimen after the mechanical polishing. You can see here the interfaces between the layered structure that you want to investigate, okay? And then we will now need to remove the damaged layer of this step here, okay? Because when you do this polishing, you attack a lot the properties, structural properties of your material. And then you have something like this, okay? You have your material, it may be divided in three different regions. The first one where it was in contact with the abrasives. You have complete change of chemical composition and a lot of deformation of material and amorphization of the surface of the material. In a second region here, you have a macro deformed layer. You have tilt of eventual grains that you have in your material. and a very sensible increase in the dislocation density of your materials. Okay, and now here you have a 3D region where you have let's call it a micro deformed layer, that you have a weak tilt of your grains and a small growth of dislocation density. Okay, this damage that was caused by the mechanical tilting, mechanical thinning, it's about 1 micrometer in depth in your material. You need to remove all of this to continue with your sample preparation. This is the idea. Okay. Then the next preparation step will be has to remove all this damaged layer. And then 1 micrometer of material needs to go out. Then what we do, we go to the dimple grinding strategy. Okay, you have this is how a dimple grinder looks like. We have these instruments here in our lab. What we have, it's a very it's a small rotating wheel that you put your sample, your disc, in the middle of this wheel, okay? And it will rotate in this direction, okay? And your sample will rotate also. And then you have a disc with something rotating here, and it's rotating, the sample itself is rotating also. And then it will go polishing your material and removing this damaged layer. And now we use smaller abrasive particles to minimize new damage. You are just removing what was previously damaged. And then you go with a series of different abrasive pastes. All these pastes will have smaller and smaller grains of abrasive particles to have smaller and smaller damage in your sample, okay? And with this, we will finish with what? With a dimple exactly in the middle of your disc, okay? You need to be sure that your disc is exactly in the center of the grinding wheel, okay? If not, you have some, the dimple will be formed not in the center of the disc. This is very important to be in the center of the disc, okay? And then this is the way these techniques work, okay? Well, with the dimpled, dimpled sample, we go to the ion beam milling technique. We use the ion beam milling technique. What we do, the machine works in this schematic way. You put your sample inside a vacuum chamber, okay, of the machine for sure. And you have two ion guns, okay? Usually they work with argon ion, okay? And you have here an acceleration, a potential difference that accelerates these argon ions in the direction of your sample. By rotating, you may tilt your sample. You have two, let's look here. We have two guns, two ion guns, one against the other, and you put your sample in the middle, okay? If you put your sample, tilted in a way that both sides of the sample will be polished at the same time, okay? These ion beams here, they are very delocalized, they are not well focused, and then they come in all your sample, and they are taking out material very gently, okay, from the center of the dimpled disc, okay? And then you go and go and go till you have a very small hole. When you have a very small hole, you expect to have electron transparency in the border of this hole. Okay? Well, here there are some factors that will affect the ion thinning, okay? The variables are the angle of incidence, then you control with the tilting of your specimen. The smallest the angle, the gentle will be the corrosion of your sample, okay? The vacuum of the chamber, the initial surface topology, it is related with your previous preparation, the dimpling part. You have here the initial chemistry of your sample, initial orientation, initial crystallography of the surface, the beam energy, and the beam profile. Okay, the beam energy, as I told you, the larger the beam energy, the most it will affect, it will take out material per sample. The smallest the beam energy, more gentle milling will occur in your sample. Okay. As I told you also, the beam profile used to be fixed and not really localized. You focus the beam, but it's very open and it corrodes everything in your sample. Okay? Here is a device. The chemistry of the nearest surface region is changed and the material is physically damaged. Okay? By doing this preparation technique. Because you understand how it works physically. You have the ion beam, then you have for microscopy you have the electron beam. The electrons have a very small mass, and then the interaction with the sample is dealt with this small mass. But when you have an ion, you have a high mass of the accelerated object through your sample, and then it will work in something like when you have the glass, you use sand to make drownings in the glass. Everybody can imagine this. You have, you understand what? There is some sand. You accelerate the sand and you corrode the glass to make drownings and so on. It's the same idea here. You are accelerating now the ions that will shock with the surface of your sample and will remove some atoms in each collision that you have with the ion. And then, because of this, the near surface, the chemistry will be changed. Why? Because you are putting out a lot of atoms of your material. And some of them will be not as good. Some of them will be put out first than the others. You may have a differential change in your sample caused by the differences in properties of the material, the chemistry of the material. And also, there is this physical damage because you have many shocks of this ion with the surface material. It will transfer momentum to your material, and it will change the localization of the atoms in a crystalline structure, for instance. Okay? Here we have some pictures of some machines of ion milling. These are commercial equipments, okay? Here you have the PIPS, I guess it's the most famous machine of these from Gatan. And here you have two different machines from Leica for ion milling. Here we have the result of this cross-section preparation that I showed. You can see here the quantum dots, okay, deposited in the matrix. This is in cross-section, okay? Here we have strain-sensitive image contrast. Here, chemical sensitive image contrast. Then you can see here the quantum dots in cross-section in your material. Here is the preparation in plain view, okay? Here you have, as you increase the number of quantum dots on your material, you see more of these objects that are actually your quantum dots. And then you may have here, as we saw, information about the size, the distribution, spatial correlation, so on. Here you can see the height of the quantum dots, the width, and so on. Okay? This is what we get then with plan view preparation of book materials and cross-section view of the material. We have another possibility to prepare this cross-section and plane view also with the focused ion beam machining, tinning of these materials. Here is a picture of our FIB machine. Some of you maybe saw this machine. And with this machine, we can do this kind of preparation. How we do it? Here, we have this part here. Here, we have an ion column with the gallium source. And then we can accelerate the gallium ions through your sample to make the tinning, to the machining, the manufacturing of your sample. But with a very high precision. Okay, different from the PIPS machine that the beam is delocalized. Here you can make a very focused beam with about tenths of nanometers of resolution. You can do the nano manufacturing of samples, sample preparation, and so on. Okay? How it works, as I'm saying, we can do the preparation from a book material in this way that I was told you. We have inside the microscope two guns, one electron gun and one ion gun. They are in angle one with each other, okay? And how to work? I will show a video in the next slide about it. I will just go very quickly here. We have first, you need to prepare a pad of platinum on the surface of your material. Well, actually, you can choose different metal sources, but we used to use platinum. It's most conventional. Okay. You do this pad on the surface. Here is where you are interested in getting your layer, okay, and your lamella, your PM lamella, and then you prepare this pad. You put a platinum bar on this pad, and then you prepare. You start with the FIB, with the ion gun, you prepare a trench in one side of your lamella, a trench in the other side, and then you cut this lamella, you cut the lamella in all the sides to make it fixed just for these two parts here. And then you can do the thinning of this lamella, and then it reveals this structure in the cross-section of the material. I will show a video of a sample preparation that's very interesting because it shows the first, from the material, from the bulk material till the sample prepared, all the steps, and you see information about the time required to do it. Okay, and then here we are. Let me just go. This is from this lab here in Italy. Okay, lab of electron microscopy of this university. Let's start. It's a metal part. It's very interesting because of this. Let's see. This is what they want to do to investigate this sample. And then you need to cut the sample. Oh, sorry. You need to cut the sample. In a saw, you section the sample. You mount the sample on the grid to go to inside the microscope. The microscope is very similar to what we have here. Is a focused ion beam also. Here you have both sides, the sample, both sides of this cylinder, okay? You just close the machine and start the game. Here you have both ion sources. Here, ion source and electron source, sorry. Here you do the platinum deposition, okay? That bar that you need to do. Here, start the regular cross sections. The idea is to make trenches in both sides of the lamella that you want to study, the cross section, okay? And then it goes excavating the material. And then people do the cleaning of this cross section. Here we have 20 micrometers in lateral dimension and 10 micrometers in this direction. Now you have a lamella ready for extractions, very thin now. Then you need to make all the changes, geometric changes in the sample. You prepare here the cutting of the lamella. You have a very small lamella, and then you cut in this way you are looking at here to the extraction, okay? Then you have a nanomanipulator. You have a very, very small tip where you put by side of your lamella. We have this precision. It's very impressive. And then, you see, you can move the lamella in a micrometer range. And then you put here, we have, you do the welding of the lamella in this manipulator by using an organometallic of platinum, the same as of the first bar. And then you cut it out and extract the lamella. Here's the time that the guy is using. Here you have the TM grid. It's a little bit different from the conventional grids. It's a half shell. And then the guy comes with the manipulator again. Now he has the lamella in the front. he attach, just touch in the sample, in the sample holder, and do the welding again, but now in the TM sample holder, the actual TM sample holder. Okay? And then it cuts out the nanomanipulator, and now he's able, or she's able to do the final tinning of the lamella. The idea is you have here the platinum deposit, the first one, okay? And you come with the tinning of this lamella to have it electron transparent. There are many, many steps. It's very hard work to do it, but with a lot of practice, people are able to do it in one afternoon or one morning. You know. Then this guy got the lamella out. Here is the system. It's similar to what we have here. Okay. He's transferring the sample to the TM sample holder and going to the TM to start the session. And this is the world record of sample preparation. Okay, just 2 hours and 15 minutes. He was possible to do it. Okay, people, I will stop this. No. Yes. Okay, let's continue. This, what I showed, it was the best video that I got in the internet. The time, it's very short. People are very, very trained. They know exactly which kind of sample they are working. It's not conventional. When you get a new sample, you need to put a lot of effort, even using that sophisticated machine to prepare the sample. Here is the address. I mentioned about the radiation damage that this technique may cause. Okay, here I have a comparing the same kind of sample, but a comparison. You can see here how your sample will look in the TM machine by using different energies of the ion beam source, okay, for the preparation of the fib lamella. Here you have a comparison between 30 kV for the preparation, 5 kV and 2 kV, okay. The final step, the ion of the thinning of the lamella, if you use 30 kV ion beam energy, you got this kind of sample. If you lower the energy to 5 kV, you have something like this. 2 kV, you get something like this. As you go to smaller and smaller energies, you have a smaller damage on your sample. This is the idea. All these steps that we use to prepare the sample will damage the sample in some way, okay? And then the final steps need to be very, very may not be too harsh to the sample. Need to be very mild to the sample. You understand this? Okay. Okay. Please, if you want to ask something, please ask. It's okay. Okay. Well, you see, it's clear that the smallest energy you have the best resolution in the TM machine. For sure, by experience, this is it's more difficult than this in the preparation step. to do this this excellent polishing, you need to put some effort. You not got it in 2 hours and 15 minutes for sure. You need to go and go effort. Yes, you need a lot of time. With that preparation that was shown, you get something like this, not something like this. Okay. Talking about radiation damage again, here we have, this is, it was an experiment that was done, okay? You have here a material, a copper bulk material that was sputtered with gallium ions, okay? At 30 keV for a long time, okay? Here we have the STM of the sample that was prepared. Here you can see the profile of percentage of gallium ions in the sample. But look, the sample is a bulk material of copper, but the guy is measuring here gallium. Why gallium? There was publications in the literature talking about the gallium and so on, because people was not, the former times, not aware of this implantation of the gallium ions inside the material, because you are using accelerated gallium ions to put out the atoms of your sample. Some of the gallium atoms, the gallium ions, will go inside your sample and will stay implanted in your sample. And then it's common, we expect to have, when you use this kind of technique, to have some gallium in the near surface of the worked material, okay? Here, if you see, it's very difficult to see, but you can see an interface here, okay? That it's about 200 nanometers, okay? That is very clear in this experiment here. This is an EBSD image of the same material. You can see here the dimension, it's about 200 nanometers also. There was a change in the orientation of the crystallites that compose this material that was caused by the action of the accelerated gallium ions. Okay? Then it's just to you to be aware that this technique is very, very nice, but you have this kind of damage that it's caused in your material. Here now I will talk about the difference. It's very interesting. Here you have, when you are very optimistic, 2 hours and a half you can do the sample preparation by the FIB technique. By cross-section, the conventional preparation that I showed, you may spend something like 25 hours. I guess it's common to use more time than this also. Okay. For the FIB preparation, you have the positive possibilities that you have. Right position accuracy, you can choose exactly where you want to see your material. It's very, very nice, very high resolution. It's very small amount of time that you need to do all the experiment of sample preparation. But you have problems with radiation damage and about the cost of the machine. This machine is really, really expensive, and all the consumables that you need to have to work the maintenance of this machine, they are very expensive. And then it's not, these need to be taken in account when you start to prepare, to use this technique, okay? And the conventional preparation, you have low radiation damage, it's not, you have low cost, but you need to have a lot of time to work on your sample, and you have about any non-accuracy related to position. It's very poor in this possibility. Okay? Well, let's now go to bulk material. We were in the surface, in the layered. Now we go to bulk material. We have different possibilities here. The TM preparation for bulk materials for this surface imaging will follow exactly what we saw for plain view in the layered materials. It's about the same. You want to see the surface of a bulk material, it's just to put it on the other side and make the dimple and so on. Okay? Another possibility to prepare bulk materials is by electropolishing. We have this window method. It's very, very hard to prepare this. You need to put a lot of effort. It's not exactly trial and error, but it's based in a lot of experience, and you do not control exactly all the factors that affect your preparation. Okay? You make, you need to protect you need to cut your sample to 100 micrometers, for instance, and then you protect the sample, the side of the sample, start the polishing, and then you have a first hole, and then you protect it again, rotate it, start again to the polishing, you have it thin, and you go and go and go until you have the electron transparency. But it's usual that you do not got the electron transparency. It's very difficult to work with this technique. Okay. We have the possibility also of the chemical thinning that will work in a exactly, not exactly, but in the same framework. By using a chemical solvent of your material, you can go with the polishing of the surface. All the tips or the rugosity of your material will be removed preferentially, because the tips will be attacked first, until you have a very shiny surface, very plain surface, and it will become dissolved and dissolved until you get the electron transparency. But as I told you, it's you need to get a lot of experience with this, but it's possible to prepare following this. Okay, and here is the possibility to use this potassium hydroxide to remove the amorphized surface of feed preparated samples, and so on. There are many, many possibilities. Here I will show about the ultramicrotomy. We have the possibility to do microtomy in cryo conditions. You can cool down your specimen, your sample to liquid nitrogen temperature, where you have the material start to be very hard, very brittle, and then when you cut it with the machine, it will cut very, very you have slices, very precise slices of your material. You can get slices that are around 100 nanometers in thickness. Okay, you can do something smaller. And it is routinely used for biological samples, polymer samples, and where the samples tend to be soft. And then it's important to put the sample in the cryo temperature to make it hard to be able to cut the material. Okay, this is very nice, very important technique, because you have the chemistry of your material unchanged to go to the microscope, and it is usually used for analytical electron microscopy experiments where you get some compositional information and so on, okay? But when you use this technique, you put a lot of many forces on your material and it will deform. Then you need to be aware that the material may change. Here is how it looks like. You have here the knife. You have here a device that goes in this direction, passing through the knife. You control the movement of this device in this direction, and then it will cutting, and you have all the slices floating, and in water, you cut, and then you can get the slices and put in TM grids. Okay? Here's a comparison between ultramicrotomy against the ion milled prepared sample. You can see here that the ultramicrotomy sample, you have the preservation of the crystalline structure of this region here. That here you cannot see any non-crystallinity. Why? Because the ions, the argon ions will amorphize the material, will change the structure, the physical structure of material, and you lose the crystallinity. Okay? This is just to show a comparison. You have the possibility, if your material is cleavable, is crystalline and cleavable, you can cleave your material and make a to look at the very end of the material, at the very edge of your material. You may have this kind of observation. Here's a comparison between the cleaved sample against the ion milled sample. Cleaving, you have very few artifacts because you just cleave the material and it's perfect, almost perfect, but you cannot see too much into the material because you is really limited by the edge of the material, just the edge, because just there you have electron transparency. This is the way. But in the case of ion milling, you have a very large area for investigation. This is very good, very important. But you have artifacts in ductile materials, all the artifacts that I'm mentioning related with change of the structure of the material. Okay? Now we go to the small pieces, to the particles. Particles are very easily prepared. You can simply put the particles on the grid if your particles are electron transparent, for sure. Here we have the possibilities of grids that we may have. Okay, you have different sizes of these squares here. It is defined as mesh. The higher the mesh, the smaller the size of these squares. You have different shapes also here. You have plenty of possibilities. This is the commercial grids that you can acquire. And these grids will have the possibility also to have carbon film, lacy carbon film, silicon nitride, many possibilities of these windows to deposit your material, your particulated material. For electron transparent particles smaller than 100 nanometers, it's very easy to prepare. The sample that I showed yesterday, I just prepared it by passing the powder on the grid and blowing the DSX out. Very easy, okay? There are the possibility to suspend the particles in isopropanol. It's the most conventional liquid that we suspend it. you go to the ultrasonic bath to disperse this material and just drop a drop on your grid and leave it to dry, okay? And when it's dried, you have the particles there. You have the possibility also to dip your grid inside the suspension. For sure, some of the particles will be attached to the grid. You need to try different strategies till you find the best one for you. But it's very simple to work with this with particles, these kind of particles. Here you can see not as good, but you can see some powder here on the grid. This is an optical microscope image of particles on a grid. Okay, they are resting there. When you go, it's not the same sample, but when you go to the TM, you can see the particles directly. Okay. Then you may change the system that you work in your research for particles that you don't have problems. This is the idea. Here, if you are working with particles that are non-transparent to electrons, then you need to cut the particles. Then you need to do some strategy to make it electron transparent. And then there are many possibilities. The most conventional is to embed your particles in a resin and cut it and prepare, as we saw in the other layered structure and so on. All that strategies apply for particles also. Okay. Here, what is shown is the particles embedded in a resin, a glue here, and the strategy here is to put it, to make it thin, and to go to the ion beam milling machine to make a very thin area of the sample, electron transparent, to go to the microscope. Okay? Well, and now, if you have particles distributed in solutions, then we can use the cryogenic TM preparations. Why to vitrify the samples? With the vitrification, we can preserve the native state of your material under these ultra-high vacuum conditions that we have inside the microscope, okay? With the cryoprotection, if you make the preparation in cryogenic, the cryogenic preparation, you may have, you protect your sample from the high vacuum artifacts related with the evaporation of part of your sample. If you have some, for instance, a polymer particle that is intumesced with water, when you go to the ultra-high vacuum, it's very common to see it shrinking under the microscope, and cryoprotection cryogenic preparation will not have this possibility. Cryoprotection of organic structures against suffering severe radiation damage, okay? Because the electron beam, it's an ionizing radiation. You are, when you illuminate your sample with the electron beam, you are ionizing everything in front of the beam. And then when you do the cryogenic preparation, you will protect your sample from this ionization also. And when you cool your specimen, you reduce the mobility of reactive species. You simply freeze in time your sample. This is the idea. You preserve the native state of your sample for the investigation that you want to do. Okay? There are applications in life sciences to see molecules, proteins, viruses, cells, and so on. And in material science also, you can see self-assembly in solution. You preserve exactly the way that the molecules, the micelles, for instance, are organized in solution. Here are some photographs of our equipments for doing it. We have the plum freezer Vitrobot, FEI Vitrobot, and this is the microscope that we use for the cryo experiments. The vitrification of water. Well, to do these experiments, the cryo experiments, we need to have the water vitrified. Why vitrified? If you freeze the water, you will crystallize the water, and water will expand. You saw the ice will float in the water. If you have a cell, for instance, the cell will explode if it is freezed normally. And then you need to vitrify. You need to make it very fast. Here is 10,000 Kelvin per second need to be the height you freeze, you cool your sample to make the water to do not crystallize. This is very important. And then you can work with amorphous water, and then you have exactly what was happening. You preserve the native state of your suspension. This is the idea, okay? For the investigation, we will need to maintain, to keep the temperature of about minus 130 Celsius degrees to avoid the recrystallization of water. If you heat your sample, the water will crystallize and will damage all your experiments. And then how to do this fast cooling? How to do it? If you use liquid nitrogen, you will not be able to do it because there is a very small thermal capacity of nitrogen. Nitrogen will is very poor heat conductance, okay, and it will be just floating on the surface of your sample. It will not cool down as fast as it needs. And then we use liquid ethane to do it. We put the sample inside the liquid ethane because the thermal conductivity of liquid ethane is much, much higher than the liquid nitrogen. Okay? How to do it? We use the plum freezing system that we have. We apply in a TM grid. We apply a drop of the suspension. Okay? You go to this blotting part. You put a paper filter on the surface of this drop to make it to get some of the water out, to make it very thin on the surface of the TM grid, and then you do a very rapid immersion of this grid with this very thin layer of liquid inside the liquid ethane, and then what you get is something like this, where you have these layers here, okay, that are vitrified, they're solid, and you can look in the TM through these holes in your TM grid, okay? Here it's another possibility. If you want to stain your specimen in cryogenic situation, you simply get your sample, a drop of your suspension, put it in a staining solution, okay? You do just make it to dissolve, to mix the staining solution with your suspension, and then your particles will be stained with this kind of stains here, okay? And repeat the same procedure of cryogenic preparation, okay? Here are some commercial instruments that you may acquire. Here, these examples of successfully prepared samples. You have here block copolymer micelles. You can see it exactly as they are in solution. It's very, very interesting. You can do many things, because if you dry this sample, you will not have this structure anymore. And then cryogenic is the only way to do it. And here, in micellar solutions, you have these very nice circular micelles here. You just can see it, take a picture of it if you are in this situation in cryogenic solution. Here I will talk about very quickly about the storage of specimens. It's very common to you to have a sample that I prepared last year and it is inside my pocket and so on. It's not good, because when you go to a very thin, when you prepare all the materials in that dimensions, in nanometric dimensions, the forces, all the chemical reactivity and so on, it's very different from bulk materials. And then it's very good practice for scientific investigation to prepare your sample and look it in the microscope, work with your sample as soon as possible after preparation. It's a good advice to give you in order to minimize strange results that may change your your work. Okay? Here are some references that you may find information about sample preparation. You have the Bible of Transmission Electron Microscopy, the Carter book, I guess you heard about it. You have a chapter dedicated to sample preparation. You have some other material here. It's a modern book that I may say that it's a Bible of sample preparation nowadays. That it's this book here from Jenny Ayashi, okay, and our collaborators. There are two books. This is techniques. There are the methods also. It describes all the possibilities, and it's a very starting reference to prepare your own sample. Here are some suppliers of all that you need for sample preparation, okay? And thank you for your attention. I hope you enjoy all the course and so on, okay? Well, if you want to question something.